So, these set of lectures are on the topic of differential equations. Differential equations are basically equations that state derivatives of a function of one or more variable in terms of lower order derivatives of the same. Okay. For instance, we may have seen, just to take a simple example of a differential equation, we could take the equation of a driven harmonic oscillator, which is very often found in physics. Which has the form of So, this equation, which is an equation for a function x of variable t, involves the second order derivative of that function x with respect to t, and the equation states its value in terms of its lower order derivative, that is dx by dt, and x itself, in addition to some external function, some given function f0 sin omega t. So, such a statement is, or such a statement, mathematical statement, is an example of what we call a differential equation. In physics, most information about the dynamics of physical systems are stated in terms of such differential equations, which after all give us the rate of changes, be it first order or second order or third order. Most often it is second order, the rates of changes of a certain quantity with time. So, it is natural that we use the language of differential equation to deal with the dynamics or change of various physical quantities in time. To write down another example of a differential equation in physics, we could take the Laplace equation, or the Poisson's equation, which gives us the potential due to a certain charge distribution with density rho. Static case in this form. So, this is another example of a differential equation where the expansion of the left hand side takes the form del square v by del x square plus del square v by del y square plus del square v by del z square equal to minus rho over epsilon 0. So, this if you look at the second differential equation, it is obvious that the derivatives involved are ones in different variables, ones that involve different variables. For instance, there is a derivative with respect to x, that with respect to y, and the one with respect to z. Moreover, each of these derivatives are partial derivatives, that is, that are derivatives taken by keeping the remaining variables constant. So, These are another class of differential equations that we often deal with in physics. The first class, which involves derivative with respect to just a single variable, are often classified as ordinary differential equations. Because they involve only ordinary derivatives with respect to a single variable, in this case t, while the second one are examples of partial differential equations. For obvious reasons. It is of interest for us to understand such differential equations and to find out or to learn about ways to solve these equations to obtain the unknown quantity involved in the respective differential equation in terms of the variables. Now, this is in general not a simple task, and depending upon the complexity of the differential equation, the level of complexity of the differential equation, be it ordinary differential equation or partial differential equation, the task of solving it to find out the unknown function becomes as much more difficult. However, in these limited set of lectures, we will try to learn a few such techniques, at least by focusing ourselves into fewer examples, a certain special case, certain special interesting examples. Before we go more into the details of differential equations, it would be good to state a disclaimer at the beginning that the scope of these lectures do not include partial differential equations. That's mostly because the type of solutions involved in partial differential equations are of a different class than compared to the solutions of or the type of methods involving solving a partial differential equation are quite different from the types of methods for solving ordinary differential equations. It is always good to start with some of the simple differential equations and to understand what the process of solving a differential equation involved. So, to begin with, let us look at a very simple differential equation which gives us, let us say, the time rate of change of position of a particle with time. Let us say so, suppose we are given an equation of this type in which we are given the rate of change of position of a particle as it moves and in time, and let us see what solving such a differential equation involves. Of course, this is a very simple differential equation. It basically gives us the derivative of a certain function in terms of the variable dependence, or it explicitly gives the variable dependence of derivative of a certain function, the function in this case being x. Solving such a differential equation means integrating this once to obtain x as a function of t, and that is easily done if you integrate this, over t, and the solution has a form which involves integral of the right hand side over t plus a certain constant, which is called the constant of integration. This is easily done to obtain t square over 2 plus c, and in the process we have obtained x of t as a function of t in this form. So, as we can observe from the solution, if I am asked what the position of the particle at a certain time t, let us say t equal to 10 seconds is, I should be able to put the value of time t equal to 10 seconds here and obtain that position. Of course, the only remaining obstacle in the process is knowing the value of the constant of integration, which must be supplied externally. Provided it is supplied, I should be able to find the value of x, the position of the particle at any time that I like. In the process of solving this, we have immediately recognized a feature of solutions of differential equations. Well, the differential equation that we looked at is one which involved a first derivative of some function x of t, and when I tried to solve that, I had to integrate it once because I had to remove the derivative on the left hand side, and that process of integration gave me one constant of integration, c. So, it should be now from this we should be able to understand that if I were looking at a differential equation which involved second order derivative of x, like the one I have written here, I could try to solve that equation as well by doing integrations, and since here I have got two derivatives on the unknown function, to get rid of those two derivatives I will have to integrate twice. Every time I integrate, I will confront one constant of integration, and eventually by the time I solve a differential equation of this type, we could expect that the solution I get for this will involve two constants, each being a constant of integration, whose values will have to be supplied to us by some means. So, these are general features of some of the differential equations that we look at mostly. So, it is time to sort of start classifying these differential equations by various classifications that we have, and then try to look at various methods that would help us to solve these differential equations. So, let us begin by classifying these differential equations. First thing that we should learn as far as an ordinary differential equation is concerned is its order of differential equation. Order of a differential equation is the order of the highest derivative term in that differential equation. So, for instance, if you look at this differential equation, the highest derivative term involved in it is dx by dt, which is a first derivative of x with respect to t, and hence I would call this equation a first order differential equation. On the other hand, this equation that I had written down initially has as its highest order derivative a second order derivative of x with respect to t. Hence, this would be classified as a second order differential equation. Now, this statement about the order of the differential equation holds true even for partial differential equations, although we are not going to deal with partial differential equations due to time constraints or time limits, the limitations with time that we have for these set of lectures. In physics, it is very often found that the equations, the differential equations that we encounter are mostly of second order or lower order. These are due to certain very special physical consequences of solutions to, or where there are certain special physical features that solutions to second order differential equations display. We won't go into details of it. However, we could also consider differential equations that involve higher order derivatives like third order, fourth order, or any higher order that we may like. Whatever classification and features of the solution that we say should continue to hold even in those cases. Now, having seen the couple of examples of differential equations and example of at least one example of solving at least one of the differential equations, now it is time to absorb some of the lessons that we learned and look forward to the general feature of solutions to differential equations that we will come across very soon. Specifically, if we look at this particular differential equation that we have solved, we could see that the solution we obtained, written here, is a function of the variable t. Now, I could choose to plot this function as a function of variable t by taking the variable t along the x axis and choosing the function on the y axis. It is clear that this particular function will have the form of a parabola, which would be furthermore easier to see if I set c equal to 0. However, even for c not equal to 0, it is a parabola. Only difference is that the value of c determines where the parabola meets the y axis. It basically gives us the y intercept. For instance, if I set c equal to 0, we get a parabola of the form shown here, where the y intercept is at the origin. On the other hand, if I set c equal to 1, I get a parabola which has its y intercept at y equal to 1. So, as we can see, for various values of c, we get parabolas which are all distinct from each other. In that, the value of c for them for each of them are different. So, we can say that this particular solution is a class of parabolas. Which are determined by its value of C. Often the value of C is called parameter. The constant of integration is also often called parameter. Hence, we say that class of parabolas characterized by the parameter C, parameter C. So, this is going to be a general feature even for higher order differential equations. If I were considering solution to a second order differential equation like the one I have here, I would need to do two integrations, in the process of which I will pick up two constants of integrations. If I call those constants C1 and C2, then the solutions that I get for such a differential equation would be again a class of certain curves parameterized by C1 and C2, the two constants of integration C1 and C2.